Hi, everybody. Let's see again. So let's start our class today. Yes, I agree. So that's nice. Today we will be study piezoelectric sensors. Okay. So let's most force sensors are based on an elastic or spring element. In this case, the force generates a deformation that is measured by some displacement sensor, as was discussed in previous lecture. The elasticity of the spring element determines the sensitivity of such sensor. A high sensitivity requires a large deformation, which is achieved by a low stiffness of the spring element. Such a large displacement, however, could intentionally affect the structure in which the force has to be measured. In piezoelectric force sensor, on the other hand, responds directly to an applied force. The associated deformation is in most cases negligibly small, assuring small loading errors in the force measurement. Also, force is the primary quantity that is measured by a piezoelectric sensor. Other quantities, such as pressure, strain, and acceleration, can easily be measured as well using a proper construction. Piezoelectric sensors have disadvantage too. The surface charge produced by an applied force might be neutralized easily by charges from the environment, or sometimes say airborne charges, by current leakage due to a non-zero conductivity of the dielectric, by current leakage, or just by the input resistance of the connected electronics. This makes the sensor behave as a high-pass filter for input signals, impeding pure static measurement. A further point of attention is the temperature sensitivity. There are various causes for these temperature effects. Those piezoelectric materials are pyroelectric, so they also respond to temperature changes. And secondly, a temperature change may induce crystal deformation and hence an electrical output as well. Further, when materials connected to the piezoelectric crystal have different thermal expansion coefficients, for instance, clumping parts and electrodes. In this case, the crystal experiences unwanted forces. Fortunately, as long as these charge changes are slow, they would not limit the applicability because of previously discussed intrinsic high-pass character. Usually, the elements of the transducer are kept together by clamping rather than gluing. A consequence is that the crystal becomes preloaded. In this figure shows in a very schematic way some basic construction. In the force sensor, in case of figure A, the force to be measured is directly transferred to the piezoelectric crystal. Obviously, the contraction provides a means to connect the electrode of the crystal to an external connector. It's not shown in this figure now. Usually, the case acts as the ground terminal. In a piezoelectric pressure sensor, the pressure to be measured is applied to a thin metal membrane. The total force on the membrane, that is the pressure times the active area of the membrane, is mechanically transferred to the crystal. Here the electric pressure sensors are also sensitive to acceleration because the mass of the housing produces an inertial force on the crystal when accelerated. For applications where pressure has to be measured in a vibrating or otherwise moving environment, special pressure sensors are designed with a compensating crystal to minimize the acceleration sensitivity. An accelerometer consists basically of one or more piezoelectric crystals and a proof mass, or as sometimes we call a seismic mass. Here also the mass is fixed by a preloaded onto a crystal. Figure B shows a compression mode accelerometer. This example comprises two crystals mounted back to back between the seismic mass and the base plate. One electrode is connected to the common surface of the crystal, the other to the housing. In this configuration, the crystals are electrically in parallel and mechanically in series, resulting in a double sensitivity. Moreover, some compensation for common interfaces is achieved. The shear type accelerometer shown in figure C and D contains four crystals mounted on a rectangular force. The masses and crystals are fixed between a center point force and a clamping ring as preload. The absence of moving parts allows a piezoelectric sensor to be mounted in a robust package and hermetically sealed. And this figure gives an impression of the real construction of the two accelerometer types shown in previous figure. In both cases, the main axis is in the vertical direction, where the sensitivity has a maximum value. Okay? Ideally, the sensitivity in the orthogonal direction is 0. Are you agree with me? Okay, so commercial sensors have a non-zero sensitivity in direction perpendicular to the main axis due to the construction tolerances, not well-aligned crystals, okay? Or the cross sensitivity of the crystal itself. The crystal type and orientation should be chosen such that the highest value of D is in line with the main axis and 0 for all other directions. For instance, when D is the shear type is responsible for maximum output in the third direction, the value of D and Dm should be 0, since these forces normal to the crystal may not generate an electrical output in that direction. Okay? So commercial accelerometers have a cross sensitivity that is just a few percent of the main sensitivity. When two or all three components of a force or acceleration vector have to be measured, multi-axis sensors should be applied. The earlier three-axis version usually consists of three separate sensors mounted orthogonally in a single housing, as shown schematically in this figure. The smallest dimensions of such sensors are comparable with a die and have a weight down to only 20 grams and sensitivities around 10 millivolts per G gram, where G is a gravitational acceleration. Usually in SI system, we measure in meters per square second. More recently, MEMS 3-axial accelerometers have a flooded to market, mainly for consumer products like cameras and games. They are also available with integrated interface circuits. Typical sensitivities between in measures from 10 to 100 millivolt per G, and R from 10 to 50 G in weight, gram in weight. The frequency band of a piezoelectric accelerometer is limited at the lower side of the spectrum by the shunt resistance of the crystal. At the upper side of a spectrum, it is limited by a resonance frequency, as you can see on this path. This figure shows the useful frequency range of a standard-type piezoelectric accelerometer. And here, S from omega is the sensitivity, that is a ratio between applied acceleration and electrical output. And S is a nominal sensitivity. The piezoelectrical accelerometer consists of a base plate, a seismic mass, and a preloaded crystal. The mechanical characteristics of this spring mass system fall from an equation of motion, and let's look at this first equation of motion. Here the M is the seismic mass, alpha is the damping constant, and K here is the spring constant between seismic mass and base. The natural frequency of the system, in other words, say the resonance frequency for alpha equals 0 equals omega naught. Yes, as you can see, omega naught is the square root from K over M. The damping constant of a piezoelectric accelerometer is usually very, very small. In that case, the damped resonance frequency omega in this figure, as you can see, is close to omega naught. A high resonance frequency requires a small mass M and a large stiffness K. The mass determines the sensitivity in the nominal frequency range and is chosen in accordance with the application. The resonance frequency of commercial accelerometers ranges from 1 to 250 kilohertz. The smaller the size, the higher the resonance frequency. Many different types of piezoelectric sensors exist for various applications. The smallest commercial accelerometers have a weight of nearly 20 grams and a resonance frequency about 50 kilohertz. And this table lists the major properties of several groups of accelerometers. And the next table shows some maximum ratings. Most types have a temperature range from -70 to +120 centigrade. When applying piezoelectric sensors, the following points should be considered. And first of all, materials properties depend on the electric loading, open or closed electrical terminal. And hence, all sensor properties like sensitivity as a resonance frequency, omega, depend on the load too. When mounting a sensor on an object, the latter is loaded mechanically, resulting in a change of acceleration and a resonance frequency omega. And when M is the mass of an object, M capital here, and the M small is the mass of an accelerometer, the acceleration is lowered by a factor M plus M small over M capital. And the resonance frequency by a factor over the square root from M capital plus M small, according to the previous equation, where subscribe and denote the unloaded and loaded situation respectively. Okay? These equations, all two equations, allow quick assessment of the loading effects when applying an accelerometer. The primary signal of a piezoelectric sensor is charge Q. The sensor impedance behaves as a capacitance C sub E, corresponding to the electrical capacity of a flat plate capacitor with piezoelectric dielectric. And this is all concerned under the subtopic called interface. And this simple impedance model can be extended by a resistance R sub F. Modeling a leakage current, like in this figure A, and the charge signal can be measured in two different ways. The first method is based on the relation between charge and voltage of a capacitor, and Q proportional C times V. Hence, the interface circuit consists of a voltage amplifier. In the second method, the charge is allowed to flow through an impedance, preferably a capacitor. The voltage across this capacitor is proportional to the charge. And this type of interface is commonly called a charge amplifier. A better name would be the charge voltage converter. And the next figure shows examples of these interface circuits, together with models for the sensor and the connecting cable, the part between the dotted line. It will be shown that the cable capacitance can have a substantial influence on the signal transfer of the system due to the capacitive character of the sensor. The sensor is modeled by the voltage source model, as you can see on a figure B on the right side of this slide. We calculate for both interface circuits the total signal transfer using the formula for operational amplifier configuration. And first, we consider the voltage readout, as you can see on figure A. The transfer of this circuit is given by the first equation on this side, where Rp proportional Rs over Rc. It's a parallel connection, and A equal 1 plus R2 over R1, the gain of the non-inverting amplifier. Obviously, the transfer shows a high pass character, as you can see on a figure A. For frequencies satisfying omega Rp times CE plus CC, the transfer equals CE over CE plus CC. So it is frequency independent. And we can see as a demonstrate here as a horizontal line here. The cable capacitance CC causes signal attenuation. And hence, the total signal transfer depends on the length of the cable. And this requires recalibration each time the connection cable is replaced. The interface circuit on figure B on the bottom part of this slide is better in this respect. Due to the virtual ground of the operational amplifier, the voltage across the sensor and the cable is kept at zero. Neither the cable impedance nor the input impedance of the amplifier influences the transfer and hence can be ignored. Assuming an ideal operational amplifier, its output voltage is minus Z2 over Z1. Without resistor RF, Z1 will be proportional 1 over j omega c sub e, and the 2, 1 over g omega times c sub f. And hence, the output voltage equal V naught and the minus expression C is over CF times Q over CE, which indeed does not depend on the cable properties. Ideally, the circuit with a capacitor in the feedback path behaves as an integrator. The input current flows through CF and resulting in a voltage equal to 1 over CF and equals dQ over dt. That is the time derivative of the piezoelectrically induced charge Q. Hence, the voltage across CF, as we can see, is just Q over CF, explaining the name charge amplifier. Unfortunately, the integrator does not only integrate the input charge, but also the unavoidable offset voltage and bias current of the operational amplifier. To prevent the amplifier from overloading, the feedback resistor RF cannot be left out. And this results in a transfer given by this equation here. Just as in equation from previous slide, this transfer has a high pass characteristics in a figure B. The cutoff frequency is set by the components of the amplifier only. For omega RR times CF, many times higher than 1. And the voltage transfer is CE over CF. CE over CF. And when using a high quality operational amplifier, in this case, we can get low offset and low bias current, and the value of the cutoff frequency can be chosen down to 0.01 Hz. A true static measurement of acceleration of force, however, is not possible. So, let's describe some applications. Piezoelectric sensors, force sensors, and accelerometers are available for a wide range of applications. They can be mounted on a proper places of the mechatronic construction, taking into account mechanical loading and direction of sensitivity. If only little space is available for mounting a commercial device, single piezoelectric crystals would be used. Taking note of the polarization direction, the orientation of the electrical contact surfaces, and the proper interfaces. Charge amplifiers are preferred in most cases. In this section, we present some examples of special designs of piezoelectric sensors for various applications. Coaxially stressed and cooled PVDF shows a rather strong piezoelectric effect. Let's look at this later. A straightforward design of a pressure sensor using this property is a sheet of PVDF on top of a rigid backing, making use of lateral deformation. However, the flexibility of PVDF allows the material to bend easily, so it can serve as a membrane, resulting in a much higher pressure sensitivity. Two pressure sensors sometimes designed according to this concept. A circularly shaped sheet of piezoelectric PVDF, usually 5 mm in diameter, and about 25 micrometer thickness, with metallization layers on both sides. Is clamped between two parts of a likewise circular housing made up of PVDF. The sensor is applied in pneumatic and hydraulic systems for pressures up to 200 kilopascal and temperature up to 125 centigrade, and is resistant to a wide range of chemicals. Many properties of the prototype have been determined experimentally: sensitivity to temperature and humidity, response time less than 100 microseconds, frequency range and stability over time, like aging and creep, as outlined in preceding section. The sensor element is also pyroelectric, so it responds to temperature changes as well, and shows a high pass characteristic that depends on the temperature-dependent loss factor or resistance of the membrane. Ice deposition, for instance, on overhead power transmission line and power pylon, may cause much damage, and it is useful to study the adhesion in different conditions. In some applications, PVDF is used to measure interfacial stress between ice layer deposited on an aluminum substrate. Clearly, the small thickness of PVDF, as well as its flexibility, makes the sensing material an excellent candidate for this task. It is shown that an embedded PVDF layer provides useful information about ice debonding stress and propagation. Many examples can be found in literature illustrating the versatility of PVDF as a means to measure pressure and obtain pressure images. For instance, one publication describes a system for measuring the dynamic, or sometimes called as a normal pressure, between a cast tire and the ground, and the material is used for automatic verification of handwritten signatures. Most piezoelectric accelerometers for industrial applications are designed according to these figures. The present market offers a vast variety of the type for almost any application. However, proposals for alternative designs aiming at even better performance or for particular applications appear on a regular basis in scientific literature. For instance, the advent of piezoelectric PVDF and the fast development of microtechnology motivate researchers for looking to new solutions for both old and new measurement problems. Soon after its discovery, piezoelectric PVDF was recognized as being a suitable sensing material. Moreover, the lightweight film-shaped material allows the construction of small and cheap accelerometers, which shows a sensor for acceleration up to acceleration of 50,000 grams. An angular acceleration sensor can be created as well by a special geometric arrangement of 4 piezoelectric elements. It means, in case of PVDF, and 2 seismic masses, an angular sensitivity of about 0.1 picocentigrade per radian and square second, and has been achieved by suspending a seismic mass on a sheet of PVDF. A very sensitive accelerometer has been achieved to be used for very low frequencies as a replacement for a geophone. The resonance frequency, let's look at this figure, please, amounts of 265 Hz, for a particular choice of the parameters. The sensitivity in this case is almost constant up to 100 Hz. Another way to realize small sensitive accelerometers is the use of the thin films of PZT, typically from 1 to 5 micrometers. In this case, the piezoelectric material is one of a sandwich of thin layers deposited on a silicon substrate. Other layers serve as electrodes and isolation. The seismic mass is formed by selective etching of the substrate, resulting in a mass spring system similar to the one as shown in this figure. The structure is sensitive in 3 directions, and an extensive FEM analysis of such thin film piezoelectric accelerometers, providing guidelines for the design of devices with specified properties. A different approach is followed in some publications, in which the PZT is deposited in a thick layer, typically near 50 micrometers, on an alumina substrate. This device is composed of 2 sensitive elements to compensate for temperature effect. They also serve as a seismic mask. The sensitivity can be set by an additional amplifier and is constant between 1 and 10 kHz. The reversibility of the piezoelectric effect provides solutions with a combination of actuation and sensing. Sometimes such a combined piezoelectric sensor actuator system is used to reduce vibration that may occur in precision mechatronic systems. In this example, a vapor stepper. A piezoelectric ceramic sensor, usually 1 millimeter thickness, measures vibration in a particular part of the construction, and stack of piezoelectric actuators, 4 millimeters thickness, generate a counter movement in the same part of the construction. With a proper design of the control loop, the amplitude of the dominant vibration mode is reduced by a factor of 7. Piezoelectricity is one of the many physical effects that have been explored for the realization of tactile sensors. In particular, the piezoelectric polymer PVDF has attracted much attention. The small dimensions in the directions of the force, as well as the flexibility of the material, simplify integration of PVDF tactile sensors in a robot gripper, even on the fingers of a Dexter gripper. One drawback of the material is the charge leakage. It means preventing the measurement of static images. Moreover, the material is also pyroelectric, which makes the sensor sensitive to temperature changes and gradient as well. And hence, this property could be put to use in robotics when thermal data about objects like temperature and thermal conductivity add useful information to the control system, somewhat similar to the human skin. Like other tactile sensors discussed in preceding chapters, piezoelectric tactile sensors are used for 2 important tasks: contour recognition and improving grip control. In some publications, a study on a C, as I mentioned, about 1 millimeter, piezoelectric tactile sensor is presented. The sensor is modeled as a second-order system and shows a frequency characteristic similar to the one given in this figure, with a resonance frequency of 6.1 kHz. In applications where dynamic performance matters, for instance, as an active rate of force sensors, PVDF sensors appear to be suitable devices. A common problem in tactile sensing for contour measurement is the low spatial resolution. Piezoelectric sensors suffer from this problem too. Although sensors have been realized that are able to determine the orientation of objects on a test bed equipped with a piezoelectric polymer. Piezoelectric ceramics and polymers are also applied in the acoustic domain. Application examples, including tactile sensors, will be discussed in the next lecture part on acoustic sensors. The integration of polymer technology and silicon technology offers interesting prospects for future developments of compact, high-resolution tactile sensors with integrated electronics. And let's start second part of today's lecture. It's called acoustic sensor. This lecture opens with an overview of acoustic parameters and properties. Next, the operation and performance of piezoelectric and electrostatic transducers are discussed. In the ensuing section, various methods for distance measurements are given and generally based on the TOF principle. And finally, in the application section, we discuss examples of ranging and imaging, as well as a non-destructive testing, inspection using acoustic principles, and interfacing. The primary measurement of an acoustic sensor is sound intensity. In combination with a controllable sound source, acoustic sensor can be used for measuring various other physical parameters, like distance, velocity of fluids, material properties, chemical composition, and many, many more. They are also suitable for navigation of mobile robots, imaging, like range finding and object recognition, and quality testing. In mechatronics, they mainly fulfill the task of non-contact measurement of distances and derived quantities. Similar to optical sensing systems, such acoustic sensing systems also comprise basically three parts: a source, a receiver, and a modulating medium. In mechatronics, the medium is mostly air. Many acoustic sensing systems are based on the measurement of the travel time to TOF. That is the time it takes for an acoustic wave or signal to travel a certain path. Look at this simple formula on the top: X proportional to V times T. This path is made dependent on the physical parameter to be determined, like distance. Such a time-based measurement approach is preferred over intensity-based measurements because the latter are less accurate, and the relation between distance and intensity is often affected by unpredictable sound, reflection, and scattering. Acoustic sensing has some advantages over optical sensing. The output is much less sensitive to smoke, dust, vapor, etc. No artificial illumination is required, allowing operation in the dark. And cheap transducers, transmitters, and receivers will do in most cases. Let's start our part of this lecture with an overview of acoustic parameters and properties. Next, the operation and performance of sound acoustics, sometimes in ultrasonic sensors, are discussed. In the answering section, various methods for contact-free distance measurement are given. And finally, in the application section, we discuss examples of ranging, imaging, and interfacing. In this part of our lecture, called properties of the acoustic medium. Unlike light, electromagnetic waves that can propagate in a vacuum, sound waves need an elastic medium to travel. The most common waves are longitudinal waves and shear waves. In longitudinal waves, the particle motion is in the same direction as propagation. In shear waves, the motion is perpendicular to the propagation direction. Some sensors utilize surface acoustic waves, SAW, surface acoustic waves sensing. An absorbing substance is deposited on the surface of a device on which the waves are traveling. The SAW's velocity, or surface acoustic waves, is influenced by the concentration of the absorbed matter, and such SAW devices are suitable for the chemical sense. The selectivity is greatly determined by the chemical interface. And in this lecture, we only discuss acoustic sensors for the measurement of mechanical quantities in mechatronics, where the propagation medium is generally, as you remember from the first part of our lecture, is air. Okay. Since the quality of an acoustic measurement strongly depends on the acoustic properties of the medium, we present here an overview of the major acoustic characteristics of air. But first, we give some definitions of terms commonly in the use acoustics. Any piece of vibrating material radiates acoustic energy. The rate at which this energy is radiated is called the acoustical or sound power. Sound intensity is the rate of energy flow through a unit surface area, and hence intensity is expressed as a watt per square meter. Compare the optical quantity flux. A sound wave is characterized by two parameters: the sound pressure, a scalar; the local pressure changes with respect to the ambient, and the particle velocity, a vector. The intensity is the time at variance product of these two parameters. It may vary from zero when the two signals are 90 degrees out of phase, to maximum at in-phase signals. The relation between intensity and pressure in the free field, in case when we have not reflection, is simply given by the equation, as you can see here on the slide, where P is the pressure in room mean square, or air RMS value. Rho here is the density, and V is the speed of sound. This equation is only valid in a free field. Often sound power, pressure, and intensity are expressed in decibel, dB abbreviation, which means relative to a reference value. Common reference value are P reference is 1 picowatt, I reference 1 picowatt per square meter, and P reference, threshold of hearing, about 20 micropascal. For example, for the intensity at 2 meters away from a sound source of P equals 1 milliwatt at the ground, the surface area of the hemisphere is about 25 meters. It's half of 4 PR square. Here meters should be without square. And so the intensity in decibel amounts 10 logarithm I over I reference, that it gets us 76 decibel. In the free field, pressure and intensity level are numerically the same when using the same references. But in practice, there is as difference between these two levels. Most sensors do not measure sound intensity, but sound pressure only. And note that for a sine wave, it means if it indicates a pure sound tone, the RMS pressure is equal only half square root from 2 times the pressure amplitude. So similar to the case of electrical signals. In general, the propagation speed in a material is given by equation for a VA, as we can see from this top, where C is the stiffness modulus of elasticity and rho is the specific mass of that material. For ideal gases, the expression for the speed of sound is, you may see from this second equation. Here, the theta is the absolute temperature. R capital is the gas constant, and M capital is the molecular mass. Substitution of numerical values for air, we yield third equation as this here, with eta, the temperature in centigrade. And hence, as a rule of thumb, the temperature coefficient of V is about 2% per 10 Kelvin. And this influence of air humidity is relatively small and is only relevant when high accuracy is required. The speed of sound is roughly 10 times lower than the speed of light. And hence, the TOF is easier to measure, but consequently, the measurement time is longer. Are you agree? Okay, so moreover, the much larger wavelengths of sound waves compared to light waves make it more difficult to manipulate with sound beams, like focusing or the creation of a narrow beam. Acoustic velocity differs from particle velocity u. The latter follows from Euler equation for the acceleration of a fluid, as you can see in this equation on the bottom. And for the A as a particle velocity in x direction. An acoustic wave is attenuated by molecular absorption of sound energy and by scattering. By wave gradually loses energy when propagating. For a plane wave, Peirce's law applies, as you can see, for this first equation. P here is the acoustic power in a certain place, and P naught is the power at a place delta F, farther in direction of propagation. The attenuation or damping coefficient alpha comprises two effects: absorption loss and scattering loss. In solids, the first effect is proportional to frequency, and the second proportional to the square of frequency. In gases, the second term dominates, and hence alpha in this case proportionals A times square F. The attenuation of the wave increases with square frequency. Acoustic damping also depends on gas composition. For air, it means that acoustic attenuation is affected by air humidity. And this table shows some values of damping in dry and humid air. The acoustic impedance is defined as the ratio between the acoustic pressure wave P and the particle velocity u in that wave. For a sound wave that propagates only in one direction, the acoustic impedance Z, as you can see in this expression for this case, is found to be, as you can see in this expression, Z proportional P over U, or square root from rho times C, or proportional V sub A times. This displays typical values for various materials. Clearly, air has a very low acoustic impedance. Liquids and solids are much harder materials. The acoustic impedance is an important parameter with respect to the transfer of acoustic energy between two media. Similar to light, waves which show reflection and refraction on the interface of two media with different optical properties, like refractive index, dielectric constant, and conductivity. Sound waves are also reflected at the interface of two media with different acoustic properties. When a sound wave arrives at such a boundary, part of the acoustic energy is reflected back and the remaining part enters the other medium. The amount of reflected or transmitted energy can be expressed in terms of the acoustic impedance. For sound waves, Snell's law applies to calculate the direction and amplitude of the refracted sound. In the special case of a wave perpendicular to the boundary plane, the ratio between reflected and incident power is given by this formula for R is Z1 minus Z2 over Z1 plus Z2 all in power 2. Z is acoustic impedance of the medium of the incident wave. Z that of the medium behind the boundary plane. And obviously, there is no reflection, hence total transmission, if both media have equal acoustic impedance. On the other hand, when the impedances show a strong difference, the power transmission is small. This has two important consequences for the S over N in TOF measurements, where emitter and receiver are both facing the reflecting surface. First, an airborne sound wave that arrives at a solid object reflects in the same way as the light on a mirror. Waves with an oblique angle of incidence reflect away from the direction of the emitter. So the reflected sound does only partially arrive at the receiver, which is usually placed very near the emitter. And secondly, transmission from an acoustic soft material to an acoustic hard material is poor. This applies in particular for acoustic sensors in air applications because of the wide gap between impedances of air and most sensor material. Since many systems consist of a source and a detector, the power loss occurs twice, resulting in a low S over N ratio in acoustic sensing systems. And now we're coming for the next part of our lecture course called acoustic sensors. Commonly used acoustic sensors belong to one of the following types: piezoelectric, electrostatic, electromagnetic, and magnetostrictive. The first two types, piezoelectric and electrostatic, enjoy great popularity in various ultrasonic applications, where we have frequencies above 20 kilohertz. The transduction effects are reversible, which means that an acoustic transducer must be used as a source or transmitter, as well as a sensor or receiver. TOF systems may have both a transmitter and receiver, or only one transducer alternately in use as a transmitter and a receiver. We will now derive an approximation expression for the spatial distribution of the acoustic power emitted by ultrasonic transducers. A common model for a transducer used for this purpose is the plain piston model. A circular disc vibrating in thickness mode. Let's look see in this picture. Each element ds, as you can see here on the blue parts of the disc sockets, acts as a point source for acoustic waves. The sound intensity of any point P in the hemisphere around the piston can be calculated by summing all contributions to the pressure variations in that point from each of point source we have here as a ds. At places where the sound waves are partially out of phase, the sound intensity is low. At places where the waves are in phase, the sound intensity is high. This results in an interference pattern of acoustic waves in front of the transducer. The acoustic pressure appears to have peaks and lows in particular directions and at particular distances from the transmitter. For simplicity, we will consider two special cases: the pressure along the main axis of the transducer, in case where phi equals 0, and the pressure at a distance r far from the center for arbitrary angle phi. The acoustic pressure along a main or acoustic axis p from x, as looked at here, is given by this first expression. Here the p from north is the amplitude of the acoustic pressure on the plate surface, where we have x equals 0, and x the distance from the plate on the main axis. This is just a result of integrating the contributions to the pressure from all surface patches ds. And this figure shows a picture of the relative pressure along the acoustic axis of two cases. First case, D equals 15 millimeters, D capital, lambda 8 millimeters, and in next case, D capital 15 and lambda 1.5 millimeters. Close the emitter. The pressure shows strong pressure variations with distance. The place of the last maximum at distance x from the plate is taken as a boundary between the near field or Fresnel zone and the far field or Fraunhofer zone of the transducer. Extreme values of P from x and in these equations occurs as a x external. The maximum of the largest value x is found for k equal 0, an amount of equation for xm. Xm proportional in d capital square minus lambda square over 4 lambda. At frequencies for which the wavelength is small compared with the dimensions of the transmitter, the near field covers a range with roughly d square over 4 lambda. The typical application example of figure A with a diameter 15 millimeter, d capital 15 millimeter, and lambda L 8 millimeters, give us 40 kilohertz in air and show that the near field range is about 6 millimeters only. It means that in most mechatronic applications, in particular TOF measurements in air, we only need to consider the propagation in the far field. An important sensor characteristic is the directivity diagram, representing the sound pattern in the far field. For a circular piston, this directivity diagram is rotationally symmetric and can be represented in a plane. Imagine a sphere or circle with a radius r around the center of the transmitter. The pressure distribution over the sphere can be described by the expression for P from R and phi. P from R and phi. P from R is the pressure at a distance R. Lambda, the wavelength of the sound signal. D capital is the plate diameter. J1 is the order one Bessel function. The diagram consists of several lobes, a main lobe and side lobe. The width of the main lobe follows from the equation and approximate value for the P from H. Approximate value for angle of divergence of the cone angle of the main lobe is given by expression for sine from phi. Apparently, the ratio d capital over lambda, or expressed opposite, determines the direction selectivity of the transducer. A narrow beam is achieved by a large ratio in case when d capital many times higher than lambda. The theoretical directivity diagram derived by the last equation is just a very rough approximation, since practical transducers do not behave as a pistol. And this figure gives the directivity diagram of two real transducers, a piezoelectric and electrostatic transducer. The smaller the size of the transducer, characterized by the diameter d capital, or the larger the wavelength lambda, the more it behaves as a point source. For a narrow beam required for optimal S over N ratio, the transducer should be large compared to the wavelength. This means to obtain narrow beams, we have to choose either a large transducer, which might be impractical in many applications, or a high frequency resulting in increased damping, and therefore a reduced rate. Since actual transducers may have shapes that differ from the circular piston model, the pressure field patterns have much more complicated shapes. By special design, the beam angle can be made smaller, resulting in so-called focus probes. We will now resume the operation principle and properties of two types of acoustic sensors, most encountered in mechatronics, the electrostatic and the piezoelectric transducers. And next lecture, we will be continuing studying this topic, acoustic sensor. Okay? I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.